I'm not the wise man, so I'm not the one standing up later. I'm going to talk more about the foundations for you and Security Foundation. So obviously all of these systems run on chips, computer chips. That's made of silicon. Silicon, as you know, is made of sand. And I'm afraid to say your software is running on sand. So through this talk, I'll basically look at why that is, how it comes about that I can pretty much say it's still running on sand today. So where is cybersecurity today? This is the complicated stuff, okay? This is what you've got to do because your software is running on sand, okay? And, you know, this is a fairly well-known British organization that's worrying about how to recommend people for cybersecurity. I don't know if they're in competition with the foundation here, but it's just the first one that popped up on Google, so we have to be careful with that, John. We'll have to get the next one up. But it's, you know, the problem really, and one of the reasons that the DSbD, which we'll be coming to, sort of was kicked off, is that IoT is that biggest threat that was John described in the opening. Because, you know, in essence, if we've all been using probably Windows machines for quite a long time, and if we think of how long it took them to get to where they are with their patching and their quality, it's still vulnerable. They still have nasty bugs. They still can't get it perfect. But look how long it took that one company. Now let's look at IoT. There's going to be thousands, if not millions, of companies building such products using a large collection of different things. I did a quick search on GitHub for MQTT, and there was over 100 implementations. Now, some people will say, yes, diversity is good in security, but going to your software bill of materials and all of that thing, do you know which version's running on which device where? Okay, so that is why, obviously, that level of the domain is really important. But what can these hardware people do about it being sand? Well, one of the key things they're doing today, and obviously anybody who chooses a chip should make sure this feature exists and is turned on, is that you have a root of trust. And what that's basically doing is making sure your device will actually start running the software you think it's going to run. Okay, so let's make sure that that happens. Unfortunately, I think there's a bit of an explosion in different APIs and different ways of using it. So some mechanism to consolidate, that's good. There's obviously a thing called the Platform Security Architecture for certification of platforms that follow a certain mechanism that obviously stretches a lot wider, but it obviously covers the root of trust as well. Another area of innovations is the idea of trusted execution environments, the idea that you can start doing coarse-grained partitioning of what you want to be secure software and what you want to be insecure software. Normal software, I think, is the typical world. Trust Zone is an ARM example of that. Obviously, Synopsys here is giving you a few other examples, but really that's something that has been key historically that said, well, actually, an open platform is so insecure, there's no way I'm going to put mobile payments on there. And I remember the discussions with the finance community saying, look, we need something like Trust Zone to even be able to put money through this mobile handset. But in both of those scenarios, you're still running that software. And as I mentioned earlier, that software is running on sand. Okay? So where's that sand come from? Well, we won't look in the mine. But what I did find is that, yes, I'm a professor at Manchester University, and I'm putting up a slide that's telling you this is where it all started going wrong. But, yeah, so there's two things. One is that a computer runs code that's held in memory, and memory is just where you put your data as well. So clearly change your data and run that. You're running something wrong. And the other thing wasn't really designed to be security, but has obviously become the key thing people work at for security is virtual memory, the memory management unit. It was purely so that they could pretend that vacuum memory, or the mercury memory, could be slightly bigger than they had by putting it off to some really old storage. That's why they invented it. But look what it's being used for today. Process isolation, context switching, scheduling, virtualization, and everything else you can mention. It wasn't designed for that. It definitely wasn't designed to give you that security principles. Obviously, the hardware vendors have gone in and tried hard to put bits on it saying, oh, actually, you can't execute this page. But again, your software is vulnerable. You know, is there anybody here who would dare put their hand up and say the software that they either write or buy is bug-free? Yeah. So it's not human error. It's been human, isn't it? So while humans are doing it. So when John said automation, yes, indeed. So what happened after basically the late 50s, early 60s? Well, by the 70s, who's read this? Nobody, yeah. It's quite interesting. It's quite few people over the decades have read it. The date, October 72. It's a recipe book for all of the ways that you can exploit software running on the computers of the time. Okay? So they basically said, look, you know, in the 70s, these computers might just be getting used in critical infrastructures, might get used for commercial things. They're broken. And guess what happened? People started reading the book, started finding them, trying to fix it. So, you know, this is just what, 30 years, 40 years of basically trying to work around the vulnerabilities in the hardware SAN platform that your software runs on. So do you think you're there yet? John's already stolen my slide. No, we're not. We're nowhere near. Okay. There's actually three projects. John mentioned the Microsoft one. There's a Code 01 and one specifically on the Chrome browser. And all of them concluded that actually memory issues, the ability that that pointer can point to either code or data, and the fact that it's just an integer in the machine and you can add numbers to it and point somewhere else, is basically 70% of the ongoing vulnerabilities. And obviously a lot of these are the ones that hackers use to get into your systems, whether it's, or not it's in protected mode stuff or pure application. So what is it about memory safety that's really broken? So if we were to look at the stack, now again, I'm not the wise person fixing the top here, but if you sort of say, well, there's the users, configuration, application services, that's really where cybersecurity has to work today. It's the person that's trying to use a system or deliver a service on that system that's responsible for its cybersecurity. And like I say, they've got a hard job, but that's really the job that has to be done today. Now, there is a move, and the UK government here is actually promoting this extension of thinking to more that actually the manufacturers need to start worrying more about how they configure and build their system. You know, are they making best practice in the way they construct their software so that they don't expose a huge API, for example, put it on the internet and hope that they don't lose customer records? You know, so how do they design and implement the product to be more secure by default? And obviously, I think this community probably knows about the PSTI bill and things like that, the recent EU directive that basically is trying to persuade the manufacturing part of the chain to increase their security so that they can, you know, basically reduce the number of mistakes they expose, okay? So it's not really that they can go to zero. I don't think, you know, I've spoken to people recently writing software for aeroplanes and they found a buffer overflow the other day. They were very upset, but it was a very good opportunity to talk about the next bit, which is actually what can the hardware do rather than being sand, how can we build walls around things and change the way software runs so that it can actually help protect against what a mistake can do. Okay, so you've got that three levels. Make the system secure, design, implement, deliver it securely. You've got the middle bit is the build. It's almost John's list in reverse, isn't it? Make sure that you build them properly, and then at the bottom, what can the hardware do to help protect you from the inevitable mistakes, regardless of how much verification, because it could be a design fault, not just an implementation fault, yeah? So there's lots of things there. And the hierarchy at the bottom, this memory bit, there's about approximately one or two ways in all of the computers today how they do that. So if you can fix that foundation, then obviously you're affecting the billions of users. Okay, so rather than educating a billion users how not to click on URLs, we make it so that the URL's in a box and it can't get out regardless of whether or not you click on it. Okay, so that's the difference of this hierarchy. So let's talk a little bit more about the DSbD program. This came about basically when UKRI, as part of the then government's industrial strategy, said to industry, is there anything that's big that you can't fix as an industry? I was in ARM at the time, and we said, yeah, this security problem, it's been there for 50 years. There's no commercial incentive or return on investment for us to actually build or design a chip that has no software to run. And obviously, we can't convince the software guys to write software for a chip that doesn't exist. We need to break that catch-22. By 2019, at that point, there was 70 million of government funding, backed by about 100 million of industry, what we call co-investments. We're now at about 90 million, just under, I think, 80 something. And then we're over 200 million of investments from industry. So it's a big thing. It's coming through as a big thing. Now, in terms of, this is the government vision statement, we have to overcome that failure, break that 50 years of the way the industry built hardware, software that never talk. We all know the scenario and can't work together. And then fix that thing at the bottom of the stack so that we can actually build something a little firmer than sand. Now, I don't like using the word secure. It's more secured, okay? It's better than nothing. But I don't think there'll ever be a silver bullet from top to bottom because the attack vector will just change, yeah? But we'll talk about protecting ourselves against potential new attack vectors as well. And it's the first time I think such a thing has actually started from the core architecture of the machine. There's been lots of add-ons, you know, trust zone and the idea of putting the secure boot is introduced and these coarse grey domains. But as soon as you get into any of those protected regions, it's running vulnerable software. Okay, so that's what this one's really about. So the program itself, just quickly, and then we'll dive in a little bit more into the technology and status for you, is we've got to break the market failure, we've got to create the enabling technology, build something that looks right, that software guys can go, oh, it is a real chip. Oh, it might be real one day. Let's have a look at it, see what the impact is. Clearly, you can't do that without having the environment around it, the technology providers checking it, making sure it works. There's nothing worse. You know, one of the big reasons we haven't changed the way software runs is, will it work? Yeah, okay. And then the final one, and this is obviously one John mentioned as well, getting the end markets, the sectors, the people that are actually, you know, having to pay the money, if you like, or the cost of the cyber attacks, etc. So realizing the platform, we were very lucky to have ARM obviously move one of their core architectures as the prototype. There are RISC-V prototypes as well. And, you know, it was interesting, a few months ago now, Intel put a analysis out where they said, are these features important in a chip? And those features were these features that I'm going to talk about. And they got a unanimous message from their market as well that says yes. So fingers crossed on the fact that this technology might appear pretty much in the majority of chips in the future. But how has the technology come about? Well, I think they should have gone actually back to the 70s because Cambridge University actually had an initiative in the 70s looking at that list of things of why computers, but obviously they were not able to get that to market to change it. They started again at the beginning of, well, the end of 2010 with a program called Cherry. It's worth a Google search. There's lots of information about it. And they've been worked on it right the way up to about here, where, yes, they're only a few miles down the road from ARM, but we started talking and they said, oh, that sounds interesting. And then we obviously got it through to the bid that basically says we want to change the world. Now, I don't know if I got it later, but it's important to point out here that the core enabling concepts and IP for this are open and free, so there's nothing here that's proprietary to ARM specifically in how this works. So the solution, if you like, and obviously I'm using other people's slides here that I've put their tops and bottoms on it, if you like, is that you can start looking at compartmentalization of that software. Now, clearly there are, like I say, trust zone, you get two. One, two, yeah, you might have 16 in Intel, but really it's only a few, and the software that runs in them is vulnerable. If you could start basically going down to a byte, you know, point to a byte or a single structure and say that is a hardware protected domain with the same security that I might have in virtual memory, then you can see you can start refactoring your code to be protected in a way that even if somebody comes in with an attack that you're not familiar with, you could probably hardware protect that data or operation of the machine. And those are all given through mechanisms where they inherit rights from that trusted boot. So in other words, the software that you know that you're booting comes up and starts providing less and less privilege to the more and more components that run in the system. So this, for example, would have, if you'd encapsulated OpenSSL into one of its compartments, there would have been no way that it could go reading beyond its own memory and things like that, and you could have stopped that one dead. The other interesting thing, those kinds of bugs would have actually been predictable ones for any developers here. So it's actually easier. They become compiler and predictable errors as opposed to random runtime errors. So John mentioned this as well. I think you read some of my slides, didn't you, John? I must have been working hard. But the primary things are, let's make sure that the code works the way it was intended and not by accident. That means the pointer. Now, again, just jumping a bit techie, how many people, if I start talking about native data types of processors, are happy? Enough. Okay. So in your processor today, you've basically got your integer data type, and if you're lucky, you've got some floating points, different widths. Your pointers are basically integers, so anything you can do with an integer, you can do with a pointer, and away you go. All right? What if the computer actually had a data type called pointer, and then that pointer can only do things that are valid for a pointer, and the hardware will stop you, and making sure that you can't randomly create them if you haven't got the privilege to do it. Okay? So immediately you've got this mechanism to stop in your software, pointers doing things they shouldn't do either by accident or on purpose. So protecting yourselves from yourself and from others. Okay? The other thing you can start doing with that pointer is start putting bounds on it along with those permissions. Okay? So you can start saying, well, actually, I just want this to talk to that, be able to touch that region of memory. That bit, that bit, that bit, we're giving smaller and small permissions down as you allocate it out the heap. And then clearly the last bit of that is the hardware having a formally verified architecture that says there's no way software can touch that bit in a way that you don't expect. And that bit says it's a valid pointer. Okay? So in other words, you can get pointers which only point where they want, and they can only access the data they're granted through privilege to access. So the primitives for the security, obviously this is an instruction set architectural change. So immediately you're going, ooh, what's that mean for software portability? It means if you don't use these features, it's portable. Okay, now the minimal entry point is recompiling, the maximal entry point is you're rewriting to use all of these fine-grained compartments, okay? But you do then have to obviously change the way the implementation works, and you have to go all the way up the stack, and that's really where DSbD program is helping the industry or steering the industry in a way that hopefully we can get as much of that stack to a level of understanding at least that there is a commercial imperative for the hardware vendors to actually start building such chips. I think I've pretty much said this, so protection of memory, particularly for C++. What about Rust? Well, Rust has unsafes and is built on SAND as well, so let's be careful what we do. Rust, yes, really good stuff, really beneficial. There's performance advantages that they can push some of the checks into the hardware, but all of the unsafes and the libraries you might be linking or the operating system you're running on today is probably still built on C or C++, as we know. And there's trillions of lines of C as well, which might not ever be all rewritten in C. The 2/3 we've mentioned about the overhead, obviously the pointer's doubling its size, so there's a performance decrease associated just with the pointers, but as you'll see in a minute, there's some upsides as well. And then the compartmentalization. So, obviously, I think most people are thinking of all of this about data. Okay, so the idea that pointers point to data, yes, but don't forget you've got program counters and stack pointers as well. So what's it mean to code? Okay, gadget searching. Okay, entry point library, let's go searching for something that can do something interesting. This kind of stuff can put that in a box and say that's the only entry. So just like when you do coarse grain and you give a very small provable vector between domains of software, you can do that here as well. You get a provable interface between your library calls. Okay, we've got projects, as I'll just cover quickly, that are trying to automate this. So you literally define what the partitioning of your libraries and address space is, and it goes and puts in these formalized boundaries that you can then obviously go and verify. And there's verification tools that are looking at those. So yeah, pointer validation, and then obviously the privilege bit. So scalability of these, obviously you've got virtual memory today, haven't you? So worst comes to worst, you could put every unit of software in a different virtual memory space and do IPC between them. Anybody build a system like that? Yeah. The hardware doesn't like, the cost of a virtual machine, a virtual memory processor is actually quite high. I should just mention quickly, you can do this on microcontrollers as well. And Microsoft has actually just announced a RISC-V microcontroller with this technology in as well. So do go searching for that, or ask me if you want to know where it is. But you've got this higher level of compartments you can work with. You can say, well, that SSL, your end-to-end stops when you hit SSL, doesn't it? As proven, your SSL had vulnerabilities. Well, what about above SSL? Once you hit your host, you're on sand again. This allows you to start moving up hardware protection on your end-to-end. So obviously, I'm quite excited about the VPN project and obviously the other ones in networking on that aspect. And I mentioned previously that obviously, unlike the memory protection, which you can just recompile for, using these boxes at the moment is a manual refactoring of code. But there are some looking ways of doing it automatically. So that performance, 0 to 5% just because of the pointers, but this is one of the funded projects that's actually using this to put basically a virtual machine environment using capabilities, and you'll see the hardware resource utilization much lower, therefore much more scalable, and the performance, as you can see here, between those protected domains is approaching that of a memory copy within a process. Okay, here's your typical interprocessor IPC. We've had Google writing a paper that says it's 2 orders of magnitude faster to communicate IPC between these hardware protected domains than processes. So unsurprisingly then, we've got projects that are looking at removing the processes from the tabs in a browser, for example, and the virtual machines and all the things they do today. If it runs, here 1.5 orders, but the fact that it's significantly faster. So what's the chip look like? Oh, I have no idea how many more slides I've got. ARM sell lots of chips. They've also been working very hard. It's not just been DSbD here. They've basically got an entire development environment going on the hardware. The hardware itself is actually available. The way it's available is that there's basically been 3 mechanisms for businesses and academia to get hold of this. Funded projects. I've got no more funded projects, but I will point out there is one from the DSTL through DASA, if you're familiar with that program. They've currently got a funded program to access this board. If you're interested in that one, that's open until November. We're running a program with the Digital Catapult called the Technology Access Program. That's a small amount of funding, and it's a bit more of a handhold to get you going on a board. And then there's the final one, which is just go to our website, which will tell you, click here and we'll see if we can get you aboard or not. Okay, lots of projects, so I think these slides will be available, so do go looking at links and things and search them out if you're interested in what the rest of the ecosystem is doing. And then to close, basically, like I say, the boards are on the way. 2 parts of that. One is to give the sectors a view of, if this happened, is it going to break what I tried to do? So in other words, finding that problem in the hardware. The other is to obviously give you an insight to what's potentially coming, and some very small initial startups of actually saying, well, actually, there's a business here because we could be first. Okay, so there's a lot to go on there. Lots of software writing. Time-wise, in reality, 4 to 5 years until you can go to the go to your DigiKey and buy one, I suspect. But obviously, you could be looking at it and asking suppliers, when are you going to get your chip? When are you going to get your chip? That kind of thing. And I did actually mention the open sourcing there as well. So with that, I will be around for most of the day. Darren here has got a stand. Do come and talk to us if you want to know more or see where those URLs are that I mentioned. Thank you.